Now the way that the polarities work across the resistors, of course, is that there are drops in the direction of the current. But when we look at the voltage across the inductor, it has a voltage that it has a polarity, at least drawn in our picture, that's the same polarity as it would have had when it was resisting the voltage supply. So if you look at these, they all appear to be drops, and so according to Kirchhoff's voltage law, the voltage across the inductor as a function of time would have to be minus the voltage across each of these two resistors added together. So if I add those together and I combine those results, I end up getting that the voltage across the resistor, the voltage across the inductor as a function of time is negative 52.8 e to the minus t over 18.9 milliseconds, which is basically just telling us, that negative sign is telling us that the polarity in the picture is not the actual polarity. It's flipped the other way in order to produce that short-lived current through those resistors. Now the other part to this question asked, how would your answer change if the switch was opened back up after being closed for only 2 time constants? So everything about the first part of this problem would still be correct. So we know that we'd have to find the Thevenin equivalent circuit. We know that the current through the inductor as a function of time in the energizing process is given by this expression right here. But the difference is that if the switch is opened back up after only 1 time constant, then we would have to determine what is the current through this inductor at a time of 2 time constants, not 1 time constant. So we'd have to determine what is that current after 2 time constants, and that becomes our initial current in the circuit during the de-energizing process. So this is for the second part of the problem. And so we could plug in 2 time constants. If I put in 2 time constants, it becomes e to the minus 2, and this gives us a current value of 0.173 amps. So the way that that would affect our answers below for the second part would be that the current through the inductor as a function of time would start off with a value of 0.173 amps, and it would still have the same time constant. And then I would have to determine the voltage across each one of those resistors, similar to the way that I did before. I'm just going to plug the values in. And of course now we don't have a current of 2 amps, we have a current of 0.173 amps. So this becomes 27.7 e to the minus t over 18.9 milliseconds, and this is 18 e to the minus t over 18.9 milliseconds. And I stopped there for a minute because I realized that I wrote something incorrect earlier. So I'm just going to fix it on here. So the voltage across the inductor then, of course, is just negative both of those voltage values across the resistors added together. So this is minus 45.7 e to the minus t over 18.9 milliseconds. So let's head back for a minute, and if we look at my major mistake on here, from the first part of the problem, when the system reached steady state, the current was 0.2 amps, and for somehow I came down here and I wrote this as 2 amps instead of 0.2 amps. So this actually should have been 0.2 amps, and this should have been 0.2, and 0.2 and 0.2. Now the numbers here are actually correct numbers because I had used 0.2 in my calculations, but I had accidentally written it incorrectly. So the main thing with inductors is that the current through the inductor cannot change abruptly. So you have to determine during the energizing process what is the current that was passing through that inductor at the time when the switch is opened back up again. And if it reaches steady state, it's the steady state value. And if it doesn't reach steady state, then the current might be some other value that you have to find, and that becomes the initial current for the de-energizing state.